In this video, we're going to go through equilibrium. So many chemical reactions don't just happen in one direction, where we think of it going from reactants to products. Sometimes those products reform into reactants. Now, not all chemical reactions are reversible, like you can't unburn something. So we call these reactions reversible. And we use a double arrow instead of a single directional arrow to represent equilibrium. So in the example here, notice we have a double arrow between water in its liquid state and water in the gaseous state. So if a reaction is reversible, it's going to reach a state of equilibrium. And that's where the rates, now key term, rate of the forward reaction is equal to the rate of the reverse reaction. So that means that the products are forming at the same rate that the reactants are reforming. So the concentrations aren't necessarily equal, but the rates that they're forming are equal. So here's a very pixelated graph of what's going on. So think about when you have a reaction. So the product starts to form, and that formation will eventually taper off. The reactants will be used up, and they'll be used up sharply, but then that will start to taper off as those rates become equal. And eventually, the rates will be the same. So if you notice, at this point right here, we call that equilibrium. That's where the rates are equal. And notice, if you go back to the y-axis here, the concentration values are not the same. They're not necessarily the same. I suppose they could be the same, but in most cases they are not the same. But the rates are the same. All right, let's take a look at the first example. It says, given the reaction, A plus 2B goes to C plus D. The reaction starts with only 1 atmosphere of A and 1 atmosphere of B. There's no C or D in the flask. Sketch a graph to show the reaction proceeding to equilibrium. Upon reaching equilibrium, there is 0.8 atmospheres of A. All right, so I'm just sketching this. It's not going to be perfect here. On our y-axis, we have partial pressure. On our x-axis, we have time. So let's start with C and D. So they're starting at 0. So they are going to form, and then their amount is going to kind of taper off. Anytime we have something that's reaching equilibrium, it's going to taper off. Okay, so these are going to be C plus D. Next we have A and B. Okay, so I'm going to draw an A, and it's going to taper off like that. Now I want to point out that B has a 2 in front of it. It's the only piece in the reaction that has a coefficient. So that means that B is going to form, or sorry, B is going to be used up twice as fast. So it might look something like that. Okay, so B with that coefficient, it's going to be used up twice as fast. And we represented that in our graph by making its line go down twice as fast as A. The rate of B is going down twice as fast as A. Okay, so again, just kind of sketched that. It's not perfect, but another thing I want to point out is they reach this state of equilibrium all about the same point right here. Okay, and when you draw these graphs, that's what you want to include in your graph. They should all reach that point of equilibrium at the same point, and then all of the rates should taper off. Now I sketched this, so it's not perfect, but they should all flatten out, plateau at the same point. Okay, when the rate of the forward reaction is greater than the reverse direction, the products are being made faster than the reactants, and therefore there is a net gain in the amount of products. So you might see it represented like this, where our top arrow is going to be larger. That means that there are more products being made, and that's how the reaction works. Now the opposite is true. When the rate of the reverse reaction is greater than the forward reaction, the reactants are being made faster than the products, then there's a net gain in the amount of reactants. So you might see it represented this way, where the bottom arrow is bigger, meaning that the reverse direction, the rate is greater. Okay, so we have a reaction, and I'm just noticing that our reaction is not correctly balanced. So let's just fix a few things here. There we go. All right, so it says the reaction N2 plus 3H2, and that goes to 2NH3, is at equilibrium at 500 Kelvin. What happens to the rates of the forward and reverse reactions if some of NH3 is added at a given time? Okay. So we have a reaction and we are adding NH3. So if you recall, for a reaction to happen, you have to have particles and they have to have a collision, right? So if you have a given space, so this might represent before, if we're adding NH3 at some time, so now there are more particles. Okay, so if there are more particles of NH3, there's more possibility for a collision to occur. So since we're adding more of NH3, the rate of the reverse reaction, so going back this way, is going to increase to reestablish equilibrium. And that means the rate of the reverse reaction will be greater than the rate of the forward reaction until it reaches equilibrium. Okay, so equilibrium is kind of like a state of Zen. Our reaction wants to be at that point. So it's going to do whatever it needs to do to reestablish equilibrium. So again, this is before. We don't have very many particles of NH3. And if we add more of them, more collisions are going to take place. And like I said, the reaction is going to shift left or shift towards the reactants to reestablish equilibrium. Okay. So some reactions reach equilibrium when there are more products, while others reach equilibrium with fewer products. The reaction quotient, which is capital Q, describes the relative concentrations of a reaction species at any time. The reaction quotient can be written in terms of concentrations or partial pressures. So we use concentrations when we're talking about solutions. We think about that in terms of molarity. We're going to use pressures when we're talking about gases. Okay, so it's really important to understand the difference. So solutions, we're going to use molarity. Gases, we're going to use partial pressures. So you'll see C, subscript C, represented for concentration when we're talking about solutions. You'll see pressures, subscript P, represented when we're talking about pressures. Solids and liquids are not included because they are pure substances and their concentrations don't change with time. Okay. At equilibrium, the reaction quotient is equal to the equilibrium constant K. So we have a reaction here, and here's how we would write the quotient or equilibrium constant. So for both the quotient and the equilibrium constant expression, it is going to be products over reactants. Okay, so notice we have products over reactants. Okay, all of our coefficients become exponents. Okay, so in all cases, all of our coefficients become exponents. And a key thing right here, anytime you're writing out one of these expressions, you always want to make sure your equation is balanced. So you need those coefficients from the reaction. If your equation is not balanced, your coefficients are going to be wrong, and then your reaction quotient or your equilibrium constant expression is also going to be wrong. So make sure that you balance beforehand. So let's do an example here. It says, write the equilibrium constant expression for the following system at equilibrium. Okay. So I will tell you that this is already balanced, but your first step should always be to make sure that your equation is balanced. Okay, so since this one is already balanced, let's go ahead and write this out. So another thing that you need to check for is the state of matter. So these are all gases, so we are going to be using partial pressures. So if you go back and look really quick, when we're using gases, we're going to write either Q sub P or K sub P. So since it is asking for our equilibrium constant expression, we are going to write out Kp, and it is going to be products over reactants. Okay. So it's going to be the pressure of CO2, my categories, and then the pressure of H2O. I'm going to go back and fill in my exponents when I'm all done, and that's going to be over the pressure of C3H8, and then the pressure of O2. Okay, so I got all those filled in. Now let's go back and let's include our exponents. So on our product side, we have 3 CO2, so that becomes an exponent of 3. We have 4 H2O, so that becomes an exponent of 4. Nothing here, don't need to put a 1. And then we have 5 O2, so that becomes a 5 right there. And that's how we write out our expression.